right, welcome back to section 2.3, right? We're taking a look at inverse trigonometric functions in this section. So just as a recap of where we were, and then we'll start in on number 7 where we'd left off. We were talking about functions needing to be one-to-one in order to have inverses. One-to-one means we have to, in the case of sine, cosine, tangent, all of our trig functions actually, we have to isolate an area of the graph to look at in order to have an inverse. And so half of our functions are isolated to quadrants 1 and 2, and the other half are isolated to quadrants 1 and 4. So if you remember, sine and tangent are in 1 and 4. Cosine is in 1 and 2. The cofunctions go with them, except that cotangent doesn't. So that's sort of weird. But if you remember the graph of cotangent, you can see why it works that way. So sine and tangent and cosecant are in 1 and 4. And then cosine, secant, and cotangent are in 1 and 2. And so we had taken a look at these different graphs and isolated them in certain ways. We were looking at some examples, and we are on number 7. So, let me mention one more thing about this right here. This actually talks about the fact that if you're in the correct domain area, you can cancel the sines and the inverse sines, the tangents and the inverse tangents, and that all works great. So for sine, if you're in quadrants 1 and 4, you cancel them out and you're done. If you're in tangent, it's quadrants 1 and 4, you cancel them out and you're done. But the tricky thing happens when you're in a different quadrant than you're supposed to be in, and then you have to resituate yourself based on reference angles. And that's the last example I think that we had done last time, which was number 6. So the problem with number 6 is that 2.57 was in quadrant 2, and sine is supposed to be in 1 and 4. So we had to relocate what this angle looks like in the correct quadrants, either 1 or 4, so that we could actually take a look at what it should be. And so what we said was, hey, look, the sine value is the same if we're in this quadrant or this quadrant, right? So we had the ability to manipulate it and to do a subtraction feature to get it into the right quadrant. All right, so we're going to see some of that happen again on some of these. So there's some other things that are going to happen as well. So let's take a look at number 7. Number 7, it says the tangent, of the inverse tangent of 4. Right? So what we need to figure out is where 4 puts us in terms of our domain value. So this is a domain value for inverse tangent. Okay, so I'm going to flip back and see if I can find my inverse tangent screen because it was early on. Here we are. So take a look at the domain for inverse tangent right here. What does it say my domain is for inverse tangent? It's everything, right? I can have every single value and it works just fine. So what's that tell you about 4? Because that was our value. It's good to go, right? Yeah, it's perfectly fine that I have a 4 here. 2 more screens, 2 more. So I have a 4 here. That's in the domain. So what that means is, once again, these will be able to cancel each other out, and I'm left with 4. So let's jot down a little bit of the why for this, so that if you look back here later, you're like, why did we get to do that? Because sometimes we can and sometimes we can't. So this is happening because the domain for inverse tangent, get the n in there, the inverse tangent is negative infinity to infinity. So inverse tangent of 4, I'm going to say it exists, right? Some of our other values don't exist because they're not in the domain. This exists. So tangent and inverse tangent will, and I'm going to use the phrase in quotes because this is not a great math phrase to use, though we use it all the time. They cancel out. Okay, so in a sense, they sort of cancel each other out. They're inverses of one another. Okay, ready to try another one? Okay, we're going to look at sine and inverse sine. And on this one, we have the sine of the inverse sine of 4. Now, if you take a look back, and this, again, I'll flip back too. Why not? This one. What is the domain for inverse sine? That's the range. Yeah, for inverse sine. Sorry, there's two domains and ranges on here. So the domain for sine is the negative pi halves to pi halves, but the domain for inverse sine is actually negative 1 to 1, right? What does that tell you about 4? It doesn't work, right? It does not work. The inverse sine for 4 doesn't exist. So right here, when this is written this way, this piece right here doesn't exist. So inverse sine of 4 does not exist. Because the inverse sine domain is negative 1 to 1. And 4 isn't in the domain. So what does that mean? Well, I'm going to show you a math symbol. You guys ever seen this one before? The 3 dots like that? It means therefore. So this is a shortcut symbol in math that you see used from time to time. It means therefore. The sine of the inverse sine of 4 doesn't exist. It can't be done. Now, I'm going to flip back over here. I'll flip back on your screen in just a second. I'd like for you to notice what the difference is between this problem and 2 problems ago, the one we did at the very end of class last time, number 5. Number 6. Number 8 says sine of inverse sine of 4, and I've told you we can't do it, correct? Over here, what does it say? It says inverse sine of sine, and then it has a 2.57. What's different about the way that this is set up than the one we just did? Right. The order, let me change colors here. The order, oh, that wasn't the color I meant to do. That's not going to show up at all. Let's try this one. Try it one more time. The order of these operations is reversed. Do you see that? It's a nuance that you might not have caught the first time around. On the 2 that we did last time, we had the inverse function on the outside, and we had the original function on the inside, right? The innermost function was our sine function. And here we flipped them for the 2 that we've done today. Why does it matter? Well, it matters because I can take the sine of any value, because the domain for sine is everything, right? It goes up and down forever. I can have any sine value of any value I want. But on that graph, I can't achieve every y value, right? So when I flip it and I do it in this order and I'm asking what the inverse sine is, I can't have just any value inside of inverse sine. The values have to be between negative 1 and 1, or it doesn't make sense. Are you with me? That's a nuance that you need to be aware of, that the order of these inverses matter. Now, if everything's good to go, right, like on tangent, the inverse and the sine, if it's all in the domain, they just cancel out and it doesn't matter. And you can kind of sort of ignore the fact that the order is what the order is. But when we have an issue with something, with an inverse sine on the inside or an inverse tangent or whatever on the inside that has a domain problem, it may or may not work. You have to pay more attention. All right. Let's take a look at what's next. So what we're going to do on the ones that follow is that we're going to be taking a look at inverse properties where we see, is this the one that's listed? Yeah. It says, use the properties of inverses for all x in the domain of f inverse, and f inverse of f of x is x for all x in the domain of f. Okay, so all that notation that we'd seen before, as well as definitions of inverse functions to find the exact value of the expression if possible. So these 2 are going to look a lot like the last 2 that we did, because you see the sine, or in this case, the cotangent and the inverse cotangent, the secant and the inverse cosecant. But they're sort of giving you this awareness that the values might need to be manipulated a little bit. We might have to reconfigure which quadrant you're in. We may not, but we need to be careful that that's a possibility. Do notice that once again, on this first one, number 9 anyway, the inverse function's on the inside, right? Okay, so let's take a look at what happens when we're in an inverse cotangent of negative pi. So let's go over here to cotangent. One more back. There we go. So what is the domain of inverse cotangent? It's negative infinity to infinity, just like tangent, right? So it's a very friendly one. Tangent and cotangents are very friendly. We have an inverse that will be able to be found for every value we use, right? So just like we did on tangent over here, right, where we were able to just eliminate them, we can do the same thing for cotangent. So right here, what we have is that these cancel in much the same way that the previous one did two questions ago for tangent. So because the domain for cotangent inverse is negative infinity to infinity, then these are going to cancel. And the cotangent of the inverse cotangent of negative pi will simply be what? Negative pi. Okay, so it's very friendly when things work out nice. Cotangent and tangent have that feature. Our other 4 all have some kind of restrictions. The restrictions vary from one to the other. They all vary in somewhat different ways, but they do vary in what we can and can't have. Now, there's another difference that happens on this one. What do you notice happen on number 10 that I mentioned earlier? The inverse is on the outside. Everybody with me on that? Yeah, the inverse is on the outside. So when the inverse is on the outside, we don't have to worry about a domain value, but we do, well, I shouldn't say it that way. We have to worry about a domain value in a different way. We have to be sure we're in the right quadrant. That's what we have to do. All right, we have to be sure we're in the right quadrant. So what quadrant are we in if we are at 7 pi over 4? Y'all know this value. You've seen it and you've memorized it. Where are we if we're at 7 pi over 4? Quadrant 4, right? So this is quadrant 1. We're in 4. So at 7 pi over 4, we're about right here, correct? So we're all the way around right here. But this is secant. Which quadrants is secant supposed to be in to be able to be worked with inverse functions? 1 and 2, right? Secant and cosine, they go together, are in quadrants 1 and 2. So I'm supposed to be in quadrant 1 and 2. And if I were in quadrant 2, these would cancel out and I'd be done. It'd be just like the last problem, right? They'd be canceled out and be done. But I'm not in the right quadrant. So I need to get to the right location. All right? So right here, it tells me my secant value is supposed to be, my angle is 7 pi over 4. Let me write that in. Secant value is, the secant subangle is always 1 over x. Do you guys remember that?
Yes.
Secant value is 1 over x, cosine is x, secant is 1 over x. So if we're down right here, this x value, where else do I have an x value that's going to be the same as this one? Which quadrant? It's actually in quadrant 1, right? The x value is going to be the same if I go straight up. So the quadrant that I want to be in to get the same x value is actually up here. What angle measure would it be if I'm going to move up here and be at the same x value? That would be pi over 4. So as we're taking a look at this, we can actually change this, and rewrite this as the secant of the inverse secant of the secant of pi over 4. Why am I allowed to change it? Because it's the same value, right? Same 1 over x value as I would have if I were in quadrant 4. Once I'm now in quadrant 1, what can I do? Yeah, these will, operate inversely. They cancel out, and I'm going to be left with pi over 4. Does that make sense? Okay, So you have to ask yourself when you're dealing with sines and cosines in particular, or secants and cosecants that are in the wrong quadrant, where will I have the right value in the right, or the same value in the right quadrant? And then I need to flip it to being in that quadrant at the correct location. Okay, you ready to do something more fun? I think the next ones are a little bit more fun. The next ones pull us back into triangles. And so if you liked the triangle approach to trigonometry, you'll like this a little bit better. What we've been doing in this last bit right here is all about unit circle kind of approach. It's not bad, it's different, okay? So we're going to take a look at what happens when we have functions that look like this. So how is this one different than the last, 6 or so that we've been doing? They're different functions this time, right? I have sine and tangent, or I'll sine and inverse tangent. But I don't have like sine and inverse sine, right? They don't match. They're not inverses of one another. Agreed? Okay. So this is how we're going to do the next, I think it's like 4 problems. They're all a little bit different than one another, is that we're going to take the piece in the middle and we're going to recognize that there's an angle that's going to come out of this, right? When I'm doing inverse functions, I'm getting an angle. Is everybody good with that? An inverse function gives me back an angle that we were at to get this value to happen. And I'm going to rewrite this instead, that the tangent, because that's what it is on the inside, of this angle is going to be this quantity 7 over 24. So I'm rewriting this in the tangent form that goes along with the inverse tangent piece I've been given. Okay, is this step okay? Because we're going to have to do this every single time where we rewrite this in this form. Okay, this is going to create for us a triangle. Okay, this tangent value is in which quadrant? 1, 2, 3, or 4. It says tangent's positive, right? Where's tangent positive? Everybody's forgotten. That's wonderful. Tangent is always positive. Well, everything's positive in quadrant 1, so everybody should at least be able to tell me 1's an option, right? Everything's positive in 1. And tangent, that is the inverse tangent, I should say, is only going to work in 1 and 4. So between 1 and 4, 1's positive, 4's negative. Okay, so we're going to draw this picture inside of quadrant 1. So as I draw this, it's going to look something like this. Then I'm going to draw my triangle in, and it's going to go like that. Okay? So I want to draw my triangle within the correct quadrant. And I need to put the 7 and the 24 along the sides of a triangle so that it makes sense. So do you remember what tangent is when we're thinking about sides of triangles? Opposite over something. Adjacent, actually. So opposite over adjacent. Okay, so the opposite then will be the 7, and the adjacent will be the 24. Okay, everybody good so far? How can I find the third side of my triangle? Pythagorean theorem. So let's call it, we usually call this side, the hypotenuse side, C. So I'm going to call it C. So we've got 7 squared plus 24 squared equals C squared. I know 7 squared, that's 49. Somebody tell me what 24 squared is. Thank you, Melody. 576. And what happens when I add 576 and 49? 625. Then what? Square root. Yep. Do you know what the square root of 625 is? It's a very nice value, actually. It's 25. So let me put this in, and I'm going to give you a name for what this is that's happened. Anytime you have a right triangle that has these integer values like that, it's called a Pythagorean triple. So you might have heard that before. If you haven't, that's fine. But there's some that come up over and over again. This is not one that comes up super frequently, but you'll recognize that there's going to be a pattern in some of them. You're going to be like, I've seen that triangle before. So the nice integer value ones do show up at kind of nice places. So, all right, so what's the point? Why did we draw the triangle? Well, let me put my angle in. Here's theta. We drew this triangle because now we have a triangle that represents the tangent of theta equaling 7 over 24. So can I find the sine of that same angle now in this triangle? I can. What is the sine in this triangle now of the angle theta? It is 7 over 25. How did you get 7 over 25, Jonas? Right. So sine is the opposite of the hypotenuse. So I did need to find the hypotenuse, right, the c value, in order to figure out how to make this work. Does that make sense? Okay. We need to make sure we're in the right quadrant. If we had been drawing this in quadrant 3 or in quadrant 4 or quadrant 2, we potentially would have had a negative on some sort of a side, and then we would have had a wrong answer by a negative. Like that would have been a possibility. So we need to take a little bit of care to make sure we're in the right place. But other than that, all the problems are going to work out just like this. So let me try another one with you. Oh, I have 2 more of these. Wonderful. That's even better. Okay. So this one's the tanverse of the inverse cosine of 1/2. So every time we're going to set the part in the parentheses to be theta. Oh, you know what? Let me make mention of something over here. Do you notice what we never did find? We never found what theta was. We didn't need to. I mean, we didn't do anything wrong. But I want you to make aware of the fact that you don't need to know what the angle is to do this problem. Right? It's a variable that's involved, but it's not ever needed to be found. Okay, so let's take a look at another one. So here we've got our inverse cosine on the inside. It's equal to 1/2, or inverse cosine of 1/2. And so we rewrite this as the cosine of theta is equal to the 1/2 that's beside it. All right, I need to figure out what quadrant I'm in. Quadrant has to be associated with a cosine value that's positive. What quadrant am I in? 1. I'm in quadrant 1, okay? If it's positive, you're going to be in quadrant 1 every single time. The negatives will tell you whether you're in quadrant 2 or 4, depending on the function. This one is positive. We're in quadrant 1. So as we're drawing our picture, we need to make sure that we draw it in quadrant 1. So the angle always comes out of the origin, okay? So this is my angle. Good grief. There we go. So here's my angle measure. And then the triangle always drops down to the x-axis. You should never be making triangles along the y-axis, okay? The triangle always comes down to the x-axis, and it creates a right angle right here. Now, cosine. Cosine is what in terms of triangles? Say it again for Melody. Adjacent over hypotenuse. So the adjacent 1 is going to be down here along the x-axis, and the hypotenuse 2 is going to be up here. Okay, is everybody good? Okay. We have a missing side. I'll call it A. You can call it whatever you want, but I'm going to call it A. So we now have 1 squared plus A squared equals 2 squared. What's 1 squared? 1. What's 2 squared? 4. And we'll subtract our 1, right? So A squared is going to be equal to 3. And then what? Square root. So my A value is the square root of 3. Now this is another familiar triangle to you. It's a 30, 60, 90 triangle in some fashion. We don't need to know that, by the way, but it is one. Kind of like you didn't really need to know that the last one was called Pythagorean triple, but it was one, okay? Regardless, we've got this triangle set up now, yes? And we would like to then find the tangent within that triangle. So what is the tangent in this triangle? How do we find tangent? Opposite over adjacent. So the opposite is square root of 3, and the adjacent is 1, so it is just the square root of 3. Okay, so we're using triangles sort of like in a forward and a backward way when we're working with these problems. Okay, I've got a third one of this. You want to try? Of course you do. Yes, of course. Okay. We've got inverse cosecant. So we'll start by identifying that this is theta and rewriting that this is cosecant of theta is equal to 8. I don't know why I didn't do any negatives. That was silly. Let's make it negative 8. Can you change it for me? Let's do that because I think we should see something that's negative. We should. Let's do negative 8. We'll make this negative here. Okay, everybody get that fixed? It really says negative 8 now? Wonderful. All right, so you can deal with cosecant of theta is equal to negative 8 if you wish. I don't want to deal with that in terms of triangles. in my world, it makes sense always to think about triangles in terms of sine, cosine, and tangent. So my inclination, whenever I see something in terms of cosecant, cotangent, or secant, is to change this into something that it's related to. So what's the reciprocal of cosecant? Sine. And if I change cosecant for sine, it means I need to take the reciprocal of the other side. So what's the reciprocal of negative 8? Negative 1 over 8. Okay, so if you want to deal with it with cosecant, be my guest, that's fine. But I'm going to change mine to sines every time because I think in terms of those better. Right? So we're going to create our triangle, but we need to make sure we're in the right, correct, that is to say, quadrant. So if I have a sine value that's negative, what quadrant am I in? I'll tell you what, it's not 1. It's either 2 or 4. I've got some people saying 2 and some people saying 4. Think about sine. Where do I have sine values that are negative? Is it in quadrant 2 or is it in quadrant 4? It's in 4. 4. We'll go like this. It's in quadrant 4. Remember, sine values are y values. So the y values are negative in quadrant 4. So I am down here actually in quadrant 4. Now it tells me that I have negative 1 over 8. Sine is what in terms of triangles? It's opposite over hypotenuse. Good. So in terms of my triangle, the opposite side over here is now my negative 1. And the negative does need to go on that side, right? That side's negative because I'm down from the x-axis. It's a negative value there. And then the hypotenuse, which is always positive. I think I just wrote it wrong, didn't I? Sorry. Negative 1 is what it's right. The hypotenuse, which is always positive, is going to be the 8 in this picture. Okay? This is the only triangle we've done so far that's not a fun little one that we've seen something like. Okay? We can still find the third side. Again, I'll call it A. Call it whatever you would like. I need A squared plus, technically it's negative 1 squared, is equal to 8 squared. Okay, so y'all told me that what's negative 1 squared? 1. That's 1. Okay, positives come out of squaring. And what's 8 squared? 64. We'll subtract the 1 from both sides, so A squared is 63. Now what? Square root. A is the square root of 63. Does it simplify? It does. Do you know, what was it, Anna? Yeah, it's 3 squared is 7. Let me remind you how that simplifies if you're like, wait a minute, how'd that happen? We would take the 63 and we would break it down. It's 9 and 7, and 9 is 3 and 3. So if we have repeated factors, right, 3 squared, it comes out of the radical. That's my 3 at the front. 7 is a single alone factor. He stays underneath the radical. You do need to simplify your radicals. 3 squared is 7. And sometimes they'll have you change them into decimals too. That's fine. So in general, though, we'll leave them with an actual value, an exact value, which would be 3 squared is 7. So right now, we have A, which is 3 squared root 7. And we're supposed to end this problem by finding the cotangent. Okay, so we want the cotangent of theta. So what is cotangent of theta? Yeah, so tangent would be opposite over adjacent. So if you want to change it, you could. But if you want to just flip it, then the cotangent would be, adjacent over opposite. Did I get it written right? I think I did. I told you I don't do triangles with the other functions quite as well. Okay, we've got a picture though, right? So my angle theta is always the central angle. It's right here. So according to this angle, what is the opposite side? That's the negative 1. And what's the adjacent side? The 3 squared root 7. So this one's adjacent on top. So it's 3 squared root 7. Opposite across, that's a negative 1. So I actually end up with negative 3 squared root of 7. Okay, is that good? Okay, so we're going to make a slight variation for our last 2 examples. I'm going to pull up the next screen and you can tell me what is the difference between this one and the last 3 that we did. Say it louder again. There's an X. Do you see inside of there, there's an x? The last three we did had numbers inside right here in the place of where that x is. Okay? The reality is the x being in there instead of the numbers being in there makes the problem easier. And here's why. You don't have to decide what quadrant you're in anymore. You're automatically going to be drawing it in quadrant 1. That's actually very nice because that was the part collectively that we were struggling with, I think, the most, was remembering which quadrant we were supposed to draw the thing in, right? So on these, we're going to always be drawing them in quadrant 1. So that's kind of friendly. So whatever I'm drawing, oops, I didn't mean to draw it that way, is going to be in quadrant 1. Whoops, let me move this down a little bit. All right. Also, though, the rest of it's going to be the same. We're going to set this equal to theta, okay? So it's going to change this so that the tangent of theta is equal to the what's inside the interior, which is, in this case, an x now. Okay? So my triangle, always going to be drawn in quadrant 1 for these. I'll pretend for a second that that's all the way down there. It's close enough, I think. All right, and then tangent, in terms of triangles, is what? Opposite over adjacent. Now, this just says plain old x. What does that mean in terms of the opposite and the adjacent? It's over 1. The x is really just over 1. Right? So if you don't see a denominator, just make the denominator 1. You do that all the time when you're trying to add fractions together. They don't have like denominators. Maybe they don't have a denominator at all kind of thing, right? So what is the opposite then? Well, it's the x. So opposite my angle theta is x. And adjacent to my angle theta is 1. So what you gained in the fact that you could draw it in quadrant 1, you lose a little bit here because now you're dealing with a variable x. That's not a bad thing. It's just something to be aware of. I'm not going to be able to get numbers in this triangle. There's a number 1, but the other two sides are going to have variables in it. We still need to find the third side. I'm going to call it c. So 1 squared plus x squared equals c squared. And what I need you to be careful to be aware of is that it looks like there's two variables, x and c. X we already have in the triangle. I'm not solving for x. I put that in the triangle from the original problem. C was what I created of my own decision, right? That's the one that needs to not be written as c. So we're going to solve this for c. Well, 1 squared's 1. X squared's x squared, and c squared's c squared. So the only thing I can do to really simplify is the 1 part. But I want this solved for c, so what am I going to have to do? Square root. Same thing I did before, right? The process is not any different. It just looks funny when I'm done. The c looks like the square root of 1 plus x squared. Please do not tell me that that is 1 plus x. You can't distribute square roots. That absolutely does not work. And I've written it on papers before, but I want to remind you of why. And we'll do one that you can see really easily. What is 3 squared? 9. What is 4 squared? What is 9 plus 16? What is the square root of 25? 5. That does not equal 3 plus 4, does it? You cannot distribute square roots. Okay, so do not be tempted to try to oversimplify something and then do so in an incorrect way. There's nothing we can do to write this any better. It is the square root of 1 plus x squared. So over here, I'm going to draw it into my picture now. Oops. I'll just write here. It's 1 plus x squared underneath the square root. Okay, coming back to the original problem then, we're supposed to take the cosine of this triangle. What is the cosine of this triangle? Well, cosine in terms of triangles is what? Adjacent over hypotenuse. What's the adjacent? It's 1. What's the hypotenuse? It's this funny looking square root that we got, right? Square root of 1 plus x squared. Do you know what's kind of cool at this point too? You're done. Okay, so why do I get to leave that square root in the denominator? There's a really good reason. Okay, Okay, you may not like my reason, I don't care, but this is the real reason. The reason is because it's got a variable in it. Because my square root has a variable underneath it, this value will sometimes already be a value that I can take the square root of. Sometimes it will, sometimes it won't. So because we don't know that this actually is an irrational number, we don't have to manipulate and get no square roots on the bottom. So that's sort of a nice feature, right? So we have the nice feature at the front where we can draw it in quadrant 1, don't have to think about that. We've got the nice feature at the end where we don't have to rationalize anything that's got a square root in the denominator. But we've given it up a little bit here in the middle where we have values that still have variables in it. So you give a little, you get a little. You ready to try one more? Okay, let's do it. So we have the cotangent of the inverse cosecant of x over square root of 3. Okay, so we're going to rewrite this. This one is the cosecant, oops, hang on, I have to do it the same way I did, theta. This will be the cosecant of theta is equal to x over the square root of 3. Or if you wish to switch it, what would this be in terms of sine theta? Square root of 3 over x. Okay, cosecant and sine are reciprocals. What quadrant am I going to be drawing my picture in? It is in quadrant 1. So my picture is in quadrant 1, always for these ones that have x in them. Oops. There we go. And sine is what? Opposite over hypotenuse. So the opposite is the square root of 3. And then the hypotenuse, my denominator, is my x. Is it okay? All right. The side I don't know, then I'm going to give it a label. I tend to use labels for the sides of triangles as x and the hypotenuse as c. You can use whatever, the sides of triangles as a is what I meant to say, and the hypotenuse as c. So this triangle then is a squared plus square root of 3 squared equals x squared. Okay, so what is square root of 3 squared? It's just 3. We'll subtract the 3 to the other side. Now, I'm solving for a, right? I'd mentioned this last time. I'm solving this for a and not for x because a is the side that I need to figure out what it is in my picture. I should have only x's left when I figure out all my sides. No other random variables that I created, okay? All right, so what will I do then for my a at this point? Yep, I'm going to square root. So the a value is square root of x squared minus 3, which does not simplify, correct? No distributing square roots. So down here, this is the square root of x squared minus 3. Okay, this leaves me with finding then the cotangent. What is cotangent of theta in terms of a triangle? What is it? Adjacent over opposite. We had one of these earlier. So what is the adjacent in this picture? Yeah, it's that square root value I just got. So the adjacent is the square root of x squared minus 3. What is the opposite? Square root of 3. So this one is cotangent of theta. You do have to rationalize this. Melody was about to tell me. How come, Melody?
Because it's a known.
Yeah, square root of 3 is a number, right? We didn't have to do it over here because this one had a variable in that square root, right? But this one in the denominator does not have a variable. Yeah? So if you'll remember, let me move this over so I have some space. We rationalize square roots by multiplying by them. So you're welcome to go ahead and move that 3 underneath the radical. You can do that. This is 3x squared minus 9. You could also leave it as square root of 3 in front of the square root. That's probably not a big deal. And then the square root of 3 times the square root of 3 in the denominator is 3. Okay, that is it for this section.